Welcome back to our last and final video of Chem 1. Okay, so here in Chapter 9, Part 2, the next thing we're going to be looking at is the concept of standard temperature and pressure. And standard temperature and pressure is just a way to define a temperature and a pressure so that you can say at STP instead of going farther than that. So STP, or standard temperature and pressure, we have 0 degrees Celsius or 273 kelvins and 1 atmosphere. And at STP, we have something called molar volume. Okay, and so what's molar volume? Well, molar volume, so what we want to do, remember the ideal gas law is PV equals nRT. And so volume, molar volume would be the volume per 1 mole. Okay, so molar volume is, let's see, the molar volume of a gas is the volume of 1 mole of a gas. Okay, so we're going to solve for V, and then we get V then is equal to nRT over P. And we're at STP. So, and it's per 1 mole of gas. So we say, all right, well, then the volume, we have 1 mole. Okay, times R, 0.08206, and it's liter atmosphere, mole Kelvin. And our temperature, 273 kelvins. And last but not least, we have 1 atmosphere. Okay, so this is going to give us a volume. So we type this in. Okay, and we can only have 3 significant figures because we started with 273, and that gives us 22.4 liters. All right, so now let's see, okay, what does that mean? What that means is that at STP, 1 mole of any gas has a volume equal to 22.4 liters. And you can use that sometimes in gas stoichiometry, but again, only at STP. Okay, now let's look at density of gases. Now, density of gases ends up being one of the few things that will change, okay? Because most things are based only on the number of particles or the number of moles that you have, not on which gas you have. Like, it doesn't matter if you have hydrogen or helium. The volume is still based on the number of moles, even though they're different sizes. Okay, so the thing that is an intensive property does not depend on the amount of the substance present is density. Okay, and so we have this formula here for density. Density is equal to molar mass times pressure over RT, and you must have a pressure in atmospheres, a temperature in Kelvin. Your molar mass has to be in grams per mole, and your density will be in liters. And the R value that you're going to use here is the 0.08206 liters atmosphere per mole Kelvin. All right, so that leads us to a question, and it says, what is the density of fluorine gas at STP? All right, so again, we're at STP, so that's 273 Kelvin, and it's 1 atmosphere, okay? And so we know our pressure, and we know our temperature, and we know R. And so we have this M, this capital M, which stands for molar mass. And we need to find that. Okay, so the molar mass for fluorine gas, okay, well, fluorine is diatomic. So 2 times 18.998. And of course, this should be old hat. It's just that we haven't done it a little while, right? 18.998 times 2 gives us, oh, okay, good. That was one I thought I had memorized, but I needed to know for sure. 37.996 grams per mole. So now I can set up my density is equal to my molar mass 37.996 times my pressure, 1 atmosphere. Oh, and you know what? Hang on just a second. I'm going to make sure that I have enough room for my units. 37.996, and that's grams per mole. I want to keep my units in there so you can see where they cancel. And then over R, 0.08206, and it's liter atmosphere per mole Kelvin. And my temperature, 273 kelvins. Okay, so the reason I showed all that is because I want to be able to cancel some things out. So here I have moles, cancel with moles. They're in the bottom in the numerator and the denominator, so they can cancel. And now I have atmospheres to atmospheres, and those will cancel. And then here I have kelvins and kelvins, those will cancel. And look, I'm left with grams per liter. Okay, and that is the units of density for gases. So I should mention that here. So when we were doing the density of liquids was always grams per milliliter. The density for solids was always listed at grams per centimeter cubed. And the density for liquids will always be reported as grams per liter. Okay, all right, so now I can type this in, divided by 0.08206 equals, good, good. And then we'll divide again by 273. All right, so now what I get here is I get that fluorine gas at STP has a density of 1.70. And you think, well, if you're doing this, where did I get that? Well, that's because on my calculator, I get 1.6906973. And I went to 3 significant figures here because the temperature I used was 273. If I wanted more than that, then it should actually be 273.15, right? You have to think about how far out you're going, but 3 is fine. Okay, so we have 1.70 grams per liter, and that is the density. Oh, no, wait, it's not. Boy, I overrounded terribly. School is coming and getting tired. See, 1.690693, 1.69 grams per liter. All right. Dalton's law of partial pressures. So Dalton's law is basically, if you take a bunch of gases and put them all together, okay, for example, you blow up a balloon from your lungs, and that's a bunch of gases mixed together, the sum of the partial pressures of the gases lead to your total pressure. And that can be really, really useful because sometimes we can figure out how much of each gas we have and then the total, but we can also work backwards and find a partial pressure or a partial quantity of gas based on total pressure. Okay, and so then you have this formula here, just saying gas A, gas B, gas C, add them all, you get total pressure. Okay. All right, so this is kind of a graphic of what that would look like if you have one graph at 1 bottle at 300 kPa and one bottle at 600 kPa and one bottle at 450 kPa, and you put them all in the same bottle that's the same size, then you have a total pressure of 1,350 kilopascals. And we'll talk a little bit about the kinetic molecular theory of gases, and we know that the gases don't really interact, and so we can just add them up. Now, sometimes we want to be able to link total pressure to partial pressure, and the way to link a total pressure and a partial pressure is what we call a mole fraction. Okay, and a mole fraction of any gas A is equal to the moles of that gas divided by the total moles. And mole fraction will always be a decimal because they always add for 1, and it is unitless. And what that means is that there are no units. Okay, and so let's take a look at a practice problem here. And it tells us that we have 5.26 moles of hydrogen gas, and 8.34 moles of helium gas in a container that at 1.15 atmospheres. What's the partial pressure of each gas? Okay, so my step one is to find the mole fraction of each gas. So find X of H2, mole fraction of hydrogen, and the mole fraction of helium. And then it doesn't matter, it could be hydrogen, helium, hydrogen and nitrogen, argon, and whatever. Okay, because we don't care what it is, just how much there is of it. Okay, so first of all, if we have 5.26 and 8.34, then our total moles equal 5.26 plus 8.34. Okay. I don't have to do it by hand, but All right, so we have 13.60 total moles. Okay. So the mole fraction of H2 is equal to 5.26 divided by 13.60. I'm going to do that in my hand. 5.26 divided by 13.6. Okay. And this gives me a mole fraction for H2 of 0.387. And that's just all it is. Okay. We don't do other things with that. All right, now let's look for our mole fraction of helium. And so that one is 8.34 moles of helium divided by my total, 13.6. And we get 21.94. I think I added them. See, it's always good to look at your calculations. Try it again. 8.34 divided by 13.6. Oh, that looks much better. All right, and here we get 0.613. And that's my mole fraction of helium. All right, so now it wants the partial pressure. So step 2, it wants the partial pressure of each gas. Okay, so if the partial pressure is equal to XA, that means that the partial pressure of hydrogen is equal to the mole fraction of hydrogen times the total. So the partial pressure of my H2 is equal to 0.387 times 1.15. And I get 0.445 atmospheres for my hydrogen. And then the partial pressure for my helium will be the mole fraction of my helium, 0.613 times my total pressure here, 1.15. Okay. And I get 1.763 atmospheres. Now in this, okay, that also didn't work. Let me try, hang on. 1.15 times 0.613. There we go. Goodness gracious. I don't know, I'm having fumble fingers today on my calculator. 0.705 ATMs. Okay, now you have to be able to add for that total so you can check yourself. Okay, 0.705 plus 0.445 is indeed 1.15. Let's see if I can show. See, it is indeed 1.15, and that was our original total pressure. So that's one example of Dalton's law. Let's look at another example of Dalton's law, a little harder. Okay, so in this one, we have an apparatus and we have helium gas on, hang on. My annotation stuff is in the way. Okay, there we go. We have helium gas on the left. Okay, and we have nitrogen gas on the right. Okay, and we're all at 45 degrees Celsius. And it says initially the valve is closed. After the valve is opened, what is the pressure of the helium gas? So what we're doing here is we're like I can actually see in my steps that I look like I combined two problems, but that's okay. All right, so after the valve is opened, what you need to imagine is that you're going to give it enough time to equilibrate. So assume that it's going to equilibrate and imagine that this is gone. That's kind of one way to do it. There we go. We can just imagine that it's gone and just draw it like that there. And that's kind of what we're doing with this. We're drawing now that we have kind of this. See if I can, there we go. All right, back and forth now. Okay, so what this has done is this means that our new total volume is, or our final volume, that'll be important in a minute, is 9 plus 3. So we have the 9 liters plus our 3 liters, which means that we're at 12.00 liters, okay? And that's our new final volume. So here what they're doing is they're asking for the pressure of the helium gas, but I'm gonna help you find all kinds of stuff because, hey, why not? That sounds like a good idea. Okay, so first of all, you use Boyle's law to figure out what your final pressure is of each gas, okay? So, and that they're just asking for that at the beginning, but I'm going to find all kinds of things. So remember that Boyle's law is P1 V1 equal to P2 V2. Okay, so your P1 V1 comes from here. So for the helium, we have 2 times 9 equal P2 V2. Well, we don't know P2 for our helium, and I've actually changed that from P2 to pressure of helium times, okay, our total volume, 12. And that means that the partial pressure of my helium is equal to 2 times 9 divided by 12, or 18 divided by 12, which is 1.5. And as I look at this, I'm seeing 3 significant figures here. So this would be 1.50 atmospheres. Wonderful. All right, now let's go ahead and find it for nitrogen too. Why not? They're not asking for us, but we'll find it anyway. Okay, so now again, we use these same. So our initial amounts here for our nitrogen. So first we have our P1, which is at 3 atmospheres, and our V1, which is at 3 liters. And that's going to give us our final pressure of our nitrogen gas times our final volume. And because the gases are going to mix together, what that means is that they're going to share both sides. They're going to share the volume from both sides. Okay, so that means that the pressure, my final pressure of nitrogen is going to be 3 times 3 divided by 12, or 9 divided by 12, which is 0.75 atmospheres. So I don't know if you've noticed, but one of the things I'm doing here is I'm monkeying around with the sig figs a little bit because Dalton's law deals with adding. Okay, so when you're adding and subtracting, remember that what counts when you're adding and subtracting isn't the number of significant figures, but the number of decimal places. So if you've noticed already, one of the things that I am doing with Dalton's law, and I did this on the previous slide too, is I'm just going to the same number of decimal places for what I'm working on here. Okay, so for everything I've got here, I have 2 decimal places, and that's where I'm going with everything. All right, now, okay, so first of all, let me come back to this for a minute. The actual question here was, what is the pressure of the helium gas? And I found that here. Here's the final pressure of my helium gas. All right, but then clearly, like I said, clearly I was combining a couple thoughts in my head. So because I was done with that, but it's telling me step one. If my question had actually been, what is the total final pressure? Okay, now all you need to do here is you type in, okay, that our total pressure from Dalton's law is equal to the pressure from our helium plus the pressure from our nitrogen. Okay, so that's 1.50 plus 0.75. And these come together to give us a total final pressure of 2.25 atmospheres. And then you can sort of check your answer. And I always like to include a check because I think that that's really, really important. So let's take a look at what we have going on here. Our initial pressure on one side was 2 atmospheres, and our initial pressure on the other side is 3 atmospheres. That means that our final pressure has to be between, because we're not changing the volume. The volume is the total that it was before. So that means that our total pressure at the end has to be between 2 and 3. Now you can see that there's a larger contribution from the lower pressure side, which means the final pressure should be closer to the low pressure than the high pressure. And that all checks out. And that's when I can say, phew, okay, I'm done. Okay, so collecting a gas over water. If you were in the lab, and if you are in the lab, because COVID has gotten to the point where we can be in the lab again, which I'm sure that I am definitely looking forward to. For those of you that are not in the lab, I'm trying to toss in these tidbits for what you would see. But one of the labs that you would do would be to collect oxygen gas from water, from over water, okay? And when you do that, what you end up with is something called vapor pressure. And so the volume of the water displaced can be related back to the amount. So you can have this closed system where you have a reaction that creates a gas. In the case of what we used to do in the lab, the ideal gas constant, we were making oxygen. And what will happen is the oxygen will flow up through the apparatus and then down, and it'll push out the water from the chamber. Okay, and you can use that water displacement. We used water displacement in chapter 1 with density. You can use water displacement to collect gases as well. And if you're trying to figure out the stoichiometry of a reaction that produces gas, that's a really, really useful way of doing it, because it's really hard to collect gas because it escapes. It's really funny. I actually tried, when I was making all these at-home labs, I tried to collect hydrogen in a balloon. And I had this great idea that I could light it on fire on my driveway or out on the road, and it would be very exciting. It didn't happen, and it didn't work. I probably wouldn't have gone that far, but the thing is that it didn't work because I couldn't really collect hydrogen in a balloon. It just all escaped. So and that's how I'm just saying it's really hard to try to collect hydrogen. Because unless you have a system, and if you have a really good closed system, then usually it's not a variable system and it just goes in and it packs in under pressure. So it's hard to figure out how much you have. Water displacement is a really, really good way to do that. Okay, so if we're looking for the vapor pressure of water, you can say your total pressure is the pressure of the water plus the pressure of your gas. So this is your gas, and pH2O is vapor pressure. Okay, and here you have a thing. So you have a reaction producing gas, and your gas is flowing up through this tube down into the water. Okay, and it's collecting here. And so this in here, you have your total pressure, and that's what's equal to both your gas and the little tiny water molecules that have escaped, because some of the water molecules become in equilibrium as a gas above. All right. Next, stoichiometry, gas stoichiometry. Oh, I'm nowhere near done. Okay. Stoichiometry in gaseous reactions can work in the same way, but they're a little tiny bit different. one thing to remember is that you not only have a mole ratio with your species, but you have a volume ratio with your species. So what that means is, see how this is 1 N2 plus 3 H2 plus 2 NH3. Okay, well, that means that you have a mole ratio, 1 mole N2 to 3 moles H2. But you could also say that you have 1 liter of N2 to 3 liters of H2. So the mole ratio and the volume ratio are the same thing. Okay, so there's 2 different kinds of gas stoichiometry. One is mass to volume. So what do I mean by that? Okay, it says what volume? Okay, what volume? That means I know that this now is my unknown. What volume of oxygen gas, okay, so again, unknown, is required to react with 10 grams of aluminum metal? So this is my known. Okay, my aluminum metal is here. This is my known. And I have 10 grams of it. Okay, now before I look at anything else, what I need to do is I need to balance this, okay? So you're gonna have to pull out the tools that you learned from back in chapter 3 and 4, mostly in chapter 4, for a lot of this gas stoichiometry. Okay, so I see I have Al2O3, but I have O2 here. Okay, so that means that I need this to be in even numbers. So I'm going to put a 2 here. So that way I have 6 oxygens, and I can put a 3 here, and then 4 aluminum. So I have 4 aluminums plus 3 oxygens gives me 2 aluminum oxides. Great. Okay, now I am working next. So this is mass to volume stoichiometry. Whenever you have mass to volume stoichiometry, your step 1 is to do stoichiometry. Using your grams known to moles unknown. Okay, all right. So grams known, I know that I'm starting with 10 grams of aluminum. And the next thing that I needed in here is the molar mass of my known. Okay, if this is a little shaky, you might want to go back to chapter 4 and take a look at your stoichiometry, the lesson. But I know that that means 26.982 grams of aluminum per mole aluminum. Okay, times the next thing that I need is the mole ratio, 4 moles of aluminum to 3 moles of oxygen. And that's where I'm going to stop, because I'm just going to my moles unknown, and there they are there. So I know that I'm done with that part. So I say 10 times 3 divided by 26.982. And then again, divided by 4. And this tells me that I have 0.278 moles of oxygen. All right, so that's our step 1. Okay, so now let's take a look at step 2. Step 2 in mass to volume stoichiometry is to use the ideal gas law, PV equals nRT, like this. V is equal to nRT over P to determine your pressure. Okay, so then I can say, well, then the volume of, in this case, we have oxygen gas, is equal to the moles that I just found, 0.278, times my R, 0.08206, times my temperature. I'm at STP, so 273, divided by my pressure. I'm at STP, so that's just 1 atmosphere. Okay, and say 0.278 times 0.08206 times 273 divided by 1 if I want to, and I get a volume for my oxygen of 6.23 liters. Okay. And that might be an important thing to know. Maybe we're feeding it through and we want to make sure that we're not using more than we need. All right, so now we have gas stoichiometry, volume to mass. And so it's sort of going the other direction, but it's not going to be quite, it's not exactly backwards. And that can sometimes be hard. Volume to mass. All right, so again, I'm going to take a look at this and I'm going to see that I have, it says, what mass of ammonia? Okay, I know that then that this is my unknown. Okay, and then it says, can you make from 20 liters of nitrogen gas? So that's my known. And it's 20 liters. And then I have some overall quantities here, 17.8 at 1.09. So I know that that means my pressure is 1.09 atmospheres and my temperature is 17.8, but I can't use that because it's not in kelvins. So 17.8 plus 273.15 gives me 200 need to be neater, 290.95 kelvins. Okay, so when you're going from volume to mass, then your first step, okay, then your first step is to use the ideal gas law, PV equals nRT, to solve for your moles of your known, okay, to solve for moles known. And I'll even write that down. Okay, so that means we have N is equal to PV over RT. And my pressure is 1.09 atmospheres. And my volume listed here is 20 liters. And my R value 0.08206. Times my temperature, 290.95 kelvins. All right, so what's that going to give me for moles? And in this case, moles of my known are going to be moles N2. So I have 1.09 times 20, okay, divided by 0.08206 equals, and divide by 290.95. All right, so this gives me moles of my nitrogen at 0.913, and that's moles N2. Okay, now I can come here and I can see step 2. Okay, step 2 is very short, and step 2 is stoichiometry. Well, actually it's not. Stoichiometry from moles known to grams unknown. And I come up here and think, oh, that was silly. I needed to balance this. Don't forget to balance it. Okay, I need to balance it. And I've balanced this before, and I can see here I have N2. So I'm going to put a 2 there. Now I have N2, and now I have 6 hydrogens. So I'll need 3 H2 units over here to make 6 hydrogens. Now I'm balanced. Excellent. So I'm going to need that going into this. So I start with the 0.913 moles of N2 that I had here. And I don't need a molar mass of this because I'm already at moles. So my next step is my mole ratio. So here I have 1 mole of N2 on the bottom, and I'm looking for ammonia. So I'll need 2 moles of NH3 on the top. And the last piece in this, because we're going all the way to grams unknown, is a molar mass. So we have 1 mole of NH3 on the bottom, and we find our molar mass to put on the top. So I'll do my hydrogens first. It's 1.008 times 3 plus my nitrogen, 14.007. Okay, and that gives me 17.031 grams of ammonia per mole. And now I can work through all this. Okay, and what I end up getting is 31.1 grams of ammonia. So those are the 2 types of gas stoichiometry that you'll have. And if you follow those steps, then it's not too bad. All right, diffusion versus effusion. And we're just going to look at this a little bit so that you understand the concepts behind it without really diving into the math too much. Diffusion occurs when gas molecules disperse throughout a container. Effusion is a little bit more specific. It's still a form of diffusion, but it occurs when there's only a small opening. So here you've got the whole thing that it can be in, but here you have a small opening large enough for about 1 particle at a time, say, to pass through. And of course, your rate of effusion and your rate of diffusion would be totally different. So here's some examples here. And it just sort of shows you how long it is. Originally in A, our 2 gases are separated. And then we go into B, and what we find here is that, remember that the white molecules were H2 and the red ones are O2. In B, it opens, but it's only a very small chamber. So at the beginning, you see a lot more white molecules moving. You see a lot more of your hydrogen gas moving than your oxygen. Because it's so much smaller, it's going to be able to move through there a little faster. And then here on this side, you can see the larger, slower moving oxygen has caught up. So you're going to end up at first, you have an imbalance, but if you give it time to equilibrate, then they'll eventually be perfectly even, because a gas or eventually completely fills its container. And I'm actually going to call this equilibrium. We aren't going to really study equilibrium in Chem 1, but there's a whole chapter basically on equilibriums in Chem 2, and it can really be interesting. All right, another bit of diffusion and effusion, if you're thinking about it, is that if you blow up 2 balloons so that they're about the same, and you've got helium on this side and you have argon on this side, and the helium molecule is much smaller than the argon balloon. And that means that the helium is going to be able to escape much more quickly. So you can kind of compare that. If you've ever been out and about, you've gotten a helium balloon, you can bring it home with you. And if it's just a latex balloon, usually by the next day, there's nothing left to it. As opposed to if you blow up a balloon with like air from your lungs, it could sit around your house for days before the air actually escapes through the pores in the balloon. So it's just kind of another piece here that you will see greater escape, greater transport with a smaller molecule. Okay. It's a good way to think too. If we're talking right now, I'm recording this clearly during the COVID-19 pandemic, and see a lot of people saying that they can't breathe when they're in a mask, that you can't get the oxygen out, that you can't get the carbon dioxide. Well, that you can't get the oxygen in and you can't get the carbon dioxide out. And the problem with that is that oxygen and carbon dioxide are very small molecules, oxygen especially. So you're not going to have trouble with oxygen and CO2. That doesn't mean if your mask is very, very thick and you're exercising very, very heavily and you're trying to breathe through it very, very quickly and your breath is full of a lot of like water vapor, that might change it a little bit. But if you're going about your normal life, if you're shopping or visiting or whatever it is that you're doing, there should be no airflow issue in a mask at all. Okay. The next thing that we're into is the kinetic molecular theory of gases. Okay. And there are 5 postulates to this, and I want you to know it and I want you to understand it. It says that gases are composed of molecules that are in continuous motion. Okay. So basically what this means is that gases never stop moving. Okay. It says the molecules composing the gas are negligibly small compared to the distances between them. And if the gas particles are negligibly small, what this means is that if you have a gas particle that size and a gas particle this size, it doesn't matter because the space they take up is going to be much bigger than the molecules themselves. So the space they take up is the important part. The next one says that the pressure exerted by a gas in a container results from the collision between the gas molecules and the container walls. Okay, and this is true. So what happens is, so air pressure, gas pressure, whatever, are caused by the collisions that it's having with the side of the wall. I'm trying to pantomime being a mime here. And I've got my walls. Okay, that's what my hands are doing. It makes more sense in class. Okay, and that's what causes the pressure. So if you speed up your gas molecule, you'll make the collisions faster. Okay, so as you speed up the gas particles or the gas molecules, you increase the number of collisions, which is what increases the pressure. Okay, so this one is gas molecules exert no attractive forces or repulsive forces on each other or the container walls. Therefore, their collisions are elastic and do not involve a loss of energy. This is the one key point where ideal gases and real gases don't always match up. Okay, so I should come over here for a minute and just point out that this is for ideal gases. Okay, and right there you can say, okay, yes, well, nothing is ideal, whether we're talking chemistry or life, right? There is no ideal. So, and we'll look at that a little bit later as well. But when we look at where the ideal gases and the real gases get mixed up, it's right here. Okay, these are the rest of them all pretty much hold true, whether we're talking about ideal gases or real gases. Okay, but it's this one, this fourth one, where we know that it doesn't work out quite as well. All right, so then the last one here, the average kinetic energy of a gas molecule is proportional to the Kelvin temperature of the gas. What this means is that as temperature increases, we move faster. As we're moving faster, our collisions increase. Collisions increase. Okay, and that means that pressure increases. Now we know from Boyle's law, if pressure increases, then volume increases as well. And that's how the temperature increase causes the volume increase. Remember from Charles' law? So as the temperature heats up, we are moving faster. Moving faster means more collisions. More collisions with the exterior wall mean higher pressure, because that's where that comes from. Higher pressure pushes the walls out, which could mean higher volume as long as you're in a movable chamber. So this is just a picture describing the kinetic molecular theory of gases. In A here, we see a drawing of a Montan's law or Gay-Lussac's law. And it's basically showing sort of what I showed before. Here's our baseline, and here we're heating it up and causing those, okay? And that will eventually cause this to move. It'll cause the piston to move up, okay? Next, we have Boyle's law, all right? And Boyle's law says that as volume decreased, oh, here it says volume is held constant. So you'll have an increased pressure, right? I thought that looked like a movable piston, but I guess these are not. Okay, in this one, what you see is here's your baseline. Now, if you push this down and decrease the volume, you squish all the gas molecules. Once you squish all the molecules, you have an increased pressure because you're going to basically double the number of collisions that you have. And then last, in Avogadro's law, if the container pressure is held constant, that means your volume can increase. If you put more gas into it, you will have more collisions, which will cause your volume to increase. Okay. All right, the last kind of mathematical topic we have is root mean square speed. Okay, and the root mean square speed is the molecular speed of our gas molecules, okay, or molecular velocity directly related to molar mass. So look here, you can see that all of these are for nitrogen. The hotter we get, see how we're spreading out? So what we can see here is that as the temperature increases, our speed increases as well. And what we can see in this one, so xenon is heavier than helium, right? Okay. And the more we have, the faster we are moving. Okay. So the smaller our gas, so smaller gas equals higher speed. All right, let's take a look at root mean square velocity. This is the equation for root mean square velocity. U equals, so U RMS is this. All right, it's 3 times R times T over capital M, all with a square root around the whole thing. So think about it like this. All right, but it's a little bit trickier than that. Let me show you why. First of all, the R value is a new one. It's now 8.3145 joules per mole Kelvin, or Kelvin mole. A joule is a kilogram meter squared per second squared. What that means is that M, our molar mass of our gas, has to be in kilograms to match our joule. And you remember this joule per mole Kelvin, that's because once we're dealing with this speed, then we're looking at energy, that kinetic energy leading towards our root mean square speed. Okay, so our assignment here is to calculate the root mean square velocity for helium at 25 degrees Celsius. Okay, we have everything. The only thing that changes in these equations is helium. So our step 1 is to find the molar mass for our gas in kilograms. Okay, so I look at helium and it tells me that I have 4.0026 grams per mole. And now I need to convert 1,000 grams on the bottom so they cancel per kilogram. Okay, and that will give me 0.00400026, and that'll be in kilograms per mole. It should be a 0 there. All right, now my step 2, after I found that, is to calculate this. Okay, now really make sure, sometimes I have trouble, students forget to do the whole inside piece first. So make sure that you do everything in there. That's why I'm adding the parentheses here. All right, so we have 3 times 8.3145 times my temperature. Okay, and it's 25 degrees Celsius. So I know I need to do 25 plus 273. Okay, so 8, 9, so 298 kelvins. And all over 0.0040026. Okay, so what I want you to do is pull out your calculator, okay, and calculate it with me while we do this, mainly because every calculator requires slightly different keystrokes in order to accomplish something like this. Make sure that you're getting the same answer I am getting. Okay. And just so that you know, my stuff in the middle is coming out at 1857083.6, we'll say. All right. I just wanted you guys to know where that intermediate step was going. So if you're having trouble with your calculator. All right. And then when I can say, okay, once we take the square root then, and it's very open-ended. So here we have 3 significant figures. So I can have 3 significant figures. Okay. So that I have 1362.748, but 3 significant figures gives me 1,360. And our units are meters per second. That's root mean square velocity. All right, last slide of the year, or the semester, sorry. All right, and what this is doing is this is just showing us real gases versus ideal gases. And it's the pressure in atmospheres versus our Z, our compressibility factor in kilopascals. And the compressibility factor is the molar volume of a real gas divided by the molar volume of an ideal gas, okay? So if this line right through the center is our ideal gas right here, you can see just how far apart this works. And remember, we said that the main reason was because gases show more attraction for each other than an ideal gas, which an ideal gas takes into account 0 attraction. Okay, and I'm just going to kind of highlight some of these. Here you can see CO2 right here, and you can see, interestingly enough, that this takes a really big dip. When we're at, you know, the more reasonable pressure we're in takes this dip down and comes up like this, okay? And then we have our red for oxygen, and that one's right here. Okay. And then we have our hydrogen gas. So hydrogen gas is right here. In some ways, you could say that hydrogen is the most ideal out of all the gases, not because it holds to this line, but because it is a straight line with pressure, and it has a little more predictability. And then the next one here in this list is methane, and methane dips down and then shoots up. And the last one in this bunch is nitrogen, N2. And the nitrogen is the closest low down and then comes up to be the highest. So the point of this graphic is to show that there are no ideal gases. That depending on where you're at, as you approach 0, this is the only, so it seems if you look at this, you can see that at a pressure of 0 atmosphere, so in a vacuum, where there are no gases, your ideal gas and your real gases are all the same. And then you can see that at different pressures, different gases will match up with there with an ideal gas as well, but it's rare and few and far between. So there's no such thing as ideal in chemistry or in life. On that note, it's been a wonderful semester. I hope very much that I have gotten to meet each and every one of my students, and drop me a line to let me know where you're at in the future. Bye.